Okay, so by this time we've looked at how infinite sums cannot be found of arithmetic sequences or arithmetic series. Infinite sums cannot be found of geometric series where the common ratio is greater than 1. But infinite sums of geometric series can be calculated if the common ratio is between 0 and 1. Okay, so let's come up with these formulas for how we can do that. So for any geometric sequence defined by our general rule here for geometric sequences, if we want to find a partial sum, the partial sum formula for geometric series, if I want to add together n terms of a geometric series defined like this, I can do that by taking the first term and multiplying by 1 minus r to the n all over 1 minus r. Okay, again, the first term in the sum, the common ratio, the number of terms that are in the sum, right? That's why when this is an n. Now this is provided that we start with 1. Okay, but be on alert, we've talked about how, like, if you start at 0 and you end at n, there's actually one more term than this in the sum. Like if I started at 0 and ended at 4, I'd have to plug in 0, 1, 2, 3, 4. There's actually 5 terms in a sum if we start at 0. Generally speaking, for the most part, we start most of our sums at 0. Or excuse me, I'm sorry, at 1. And we'll do a couple examples. In infinite sum, remember, this is only possible with geometric series, and it is only possible with geometric series where that common ratio is between 0 and 1. A much simpler formula. So if we're doing the infinite sum of some geometric series, okay, it doesn't matter what term we're starting with, this is equal to a much simpler formula where we take the first term and we divide that by the difference of 1 and the common ratio. So in your notes you should have these two formulas prominently placed, boxes, arrows, stars, whatever. These are the formulas that we use for a geometric series. This was our formula for the partial sum of an arithmetic series. Okay, you should have all of those prominently placed in your notes. A quick little example here, right? Find the 9th partial sum of the series. Now take a look. We've taken infinity and put infinity here. That doesn't mean that we're doing an infinite sum if they're asking for the 9th partial sum. That means we're only going to add together the first 9 terms, right? The first term we get by plugging the number 1 in for n. So that first term is negative 2 to the n minus 1. Okay? Negative 2 to the n minus 1, which is 1 minus 1, which is 1. We can get that by looking in the front here. Remember, again, when it's written with to the n minus 1 power, the first term is in front of that common ratio. Okay? So we have the first term of 1. So our formula, the formula for finding the 9th partial sum, if we start at 1, for negative 2 to the n minus 1 is equal to the first term times 1 minus the common ratio raised to the 9th power all over 1 minus the common ratio. Okay, we're just typing this. At this point you can just type this into your calculator. I want to say that negative 2 to the 9th power is, let's see, I think that's 512. I'm going to go with 512. So this is equal to 1 times 1 minus. Since it's a negative number raised to an odd power, I know that's negative 512 over 1 minus a negative 2. We're going to call that 3, right? So we get a grand total of 513 over 3, which is actually equal to 171. Okay? 1 minus negative 512 is 513. We'd add these together. 513 divided by 3 is 171. So here's an example of how, even though the sum's written with an infinity symbol, they only want the sum of the first 9 terms. We have to calculate the first term. That goes here. Remember, in our formula for a partial sum, we have the first term in front of this gargantuan mess. Then we take the common ratio to the n power. Our common ratio here is -2, so we're multiplying -2 times itself 9 times. We're also plugging that down here, and we're just strictly calculating what's inside those parentheses. We get 171.